And I'll give actually, there's some complications, so I'll really just focus on one very simple example. We only have one loop to consider. Okay, so hopefully then that's sort of useful. Then you can, in case you're looking at a model that you're interested in, this will help you then have a starting point if you need to calculate, say, the CP violation in a decay. Okay, so we looked yesterday at this asymmetric dark matter model where from this hylogenesis model by Sean Tulin and collaborators. So I remind you, this was the Lagrangian with an effective operator here, coupling this Dirac fermion to sort of the neutron portal operator, and have a Yukawa coupling of the Dirac fermion with what turns out to be our dark matter sector here. Okay. Okay, and this gives you then decays x1 to udd, x1 to y bar phi star, x1 bar to u bar d bar d bar, and x1 bar to y phi, okay? Now, as you can see here, as long as we assign this, let's talk about a generalized baryon number. So this here has visible baryon number 1, and now if we assign this dark baryon number 1, so these are the antiparticles though, so Q of the dark baryon charge of y phi will be equal to -1, say, right? And then we'd have a conserved quantity which will be equal to BV plus B dark, and our broken quantity will be equal to BV minus B dark, okay? So this shows exactly that we're in this case 1 scenario for the asymmetry generation, which I discussed previously. Yeah. So then, So then, this is conserved. So then, from this we see that eta B dark will just be equal to negative eta B. Okay. So we generate through the CP violating decays I showed yesterday, we generate an asymmetry in the baryons, and an opposite asymmetry in these particles here. So we have more y phi than y bar phi bar, and they balance out. So in a way, you can then think of these sorts of scenarios as having, this generalized baryon number, and all the universe in this generalized baryon number is symmetric. Yeah? Generalized baryon number is 0, but you sort of hide the dark baryon number in the dark matter sector. Yeah? So sort of dark baryons are carrying the opposite baryon charge than the visible sector. Okay. So we saw the loops yesterday, so I won't go over the CP violation again. And now in this paper, the original paper here, so you can think, this is a Dirac fermion. If it's decay time is long, then it can go out of equilibrium. Yeah? But in the original paper, for a reason I'll get into shortly, they were interested in relatively low scales. Yeah? So they didn't just take the standard decay scenario where you have a thermal bath and things are in equilibrium, but instead they assumed that these Dirac fermions are produced in the out of equilibrium decay of a new scalar which has grown to dominate the energy density of the universe. Yeah? So in a way, they introduced this new scalar with a very long lifetime. And imagine that this decays into x bar pairs, which then, when these decay, they're out of equilibrium because they're produced through this decay here. And then this sources the baryon asymmetry, okay? So going back to a question we had yesterday about entropy production. So we assume here that at the start sort of the process of the baryon generation, this is, say, some scalar, some matter field, and if you have studied, say, axions before or something like this, or the end of inflation, this thing is just oscillating around the bottom of its potential, and if it's a m squared, phi squared type potential, then it in its coherent oscillations, it redshifts as matter. Yeah? Okay, so rho total is just, at the start, is just going to be, of our process, is just going to be equal to rho phi. Okay? And this is little phi, and this is capital phi. Yeah? So they're different fields. Okay. And anyway, then you can find a system of Boltzmann equations which tell you sort of the what goes on. And these are conveniently written like this with the scale factor here inside the time derivative. Just for convenience, you can rewrite the equations this way. So you have here the equation for the entropy production, which is now, when this thing is decaying, it's decaying into radiation, so it's producing entropy. Yeah? And then finally, here the equation for the baryon asymmetry. So this phi is sort of acting as non-relativistic matter, okay? So this here, this factor here, rho phi on m phi, this is simply the number density of the phi, yeah? So what this term is telling us is that it's just like the out of equilibrium decay, right, term that we see also in sort of leptogenesis, but with no, because this thing is so far out of equilibrium, the reverse process is completely negligible, yeah? So you see here this decay, the source of the baryon asymmetry depends on the CP violation, and then this is just the average number of x average number of x produced in the phi decay. Okay. So one can solve this numerically, but you can get a decent approximation analytically. And to do that, you set this thing decays and reheats the universe, creating a plasma. And after at reheating, the energy density at reheating is, okay, we define T reheat when rho phi here is equal to the radiation density. So you have half of the total energy density in rho phi and half in the radiation, yeah? So rho phi equals rho radiation, rho phi at T reheat, okay? And this occurs when when T is roughly 1 on gamma phi, or roughly 1 on H T reheat, okay? So this is just equating the time of the decay with the Hubble rate then. Okay. So then one can get a decent approximation assuming this, what is called instantaneous reheating, yeah? So we take this here, rho phi at reheating is equal to n phi m phi, and this n phi is going to source our baryon asymmetry, and then you can find that rho phi on S is approximately 3/4 T reheat. And for this, you just use the fact, this equation here, rho radiation is pi squared on 30 G star radiation T reheat to the 4, and S is this, with a very similar, with one less power of temperature and a slightly different prefactor, so that's where you get this 3/4. Okay, and assuming that these are approximately the same, okay? So then the baryon density is set by epsilon, the average number of these particles produced in each phi decay, times n phi, and YB is this divided by the entropy. Which gives you then, when you put everything together, 3 epsilon nx T reheat on 4 m phi, okay? And this, in the paper, they say they also have solved these equations numerically, and up to some order 1 factor. This gives you a good approximation. Okay. Now we also have to worry about washout processes when this is going on. So one washout process is that you go from Y phi like this via one of these Dirac fermions so you have an excess of Y and phi, but then you can, and an excess of baryons, but then as statistically, you'll be more likely to go then in the direction left to right than right to left because of the finite chemical potentials. So you have to make sure that such processes are suppressed, and this gives you an additional constraint. So you can estimate this sort of rate. We'll just estimate this dimensionally, right? So you put in the relevant couplings. So you have different XA, XB here possible, yeah? So there are different diagrams, yeah? Summing up, yeah, in principle. okay? And then from the first term there, from the first coupling, you know that's an effective operator. So when you square the amplitude, you'll get m, capital M to the 4. And then from this fermionic propagator, you end up getting, in this case, when you do things carefully, just a mass squared here, okay? And you can set this to be below roughly the Hubble scale at reheating, so that this process doesn't lead to washout, okay? And that going through, you know, doing this, you just find that T reheat should be below about 2 GeV when you normalize things to the TeV scale. M to the 4. This we could put MXA, MXB here. Okay. So this is, if you want this sort of scale to be low, you're looking at a low reheat temperature, yeah? Okay. Sorry, I forgot to put. Sorry, I forgot to put the power here, dimensionally. Yeah. Sorry, I just missed that. Okay. And in principle, you should check other things such as washouts, such as these sort of processes. But you can see here, this left to right process is going to be, in principle, kinematically suppressed if this is massive. And then you have to check the right to left process by looking at reheating the number density of the quarks and checking that this process is subdominant to the CP violating decay, okay? So there's some other checks to do. There are some complications because in principle you could extend this and make this CP violating as well, but we won't get into that. So this is sort of an overview of the model. So you have this out of equilibrium decay of this long-lived scalar, which reheats the universe, producing entropy and also sourcing the baryon asymmetry. And now, as we discussed briefly yesterday, you can invoke a dark U1 gauge symmetry to annihilate away the symmetric components of these dark matter particles. Basically then, once you're finished with this annihilation process, you end up, because the asymmetries are related, you simply end up with this relation. We imagine this is happening after Svaleron decoupling. And then this basically gives you that, these masses, given the kinematic constraints, okay, basically given the uncertainties here, you expect something that, given the uncertainties in these quantities, okay, guess being a bit generous as well, you expect this sort of mass range, or 1.7 my m phi. So given the kinematic constraints that we talked about yesterday, to avoid the nucleons decaying into the dark matter particles, we need these individual masses to be between 1.7 and 2.9 GeV. And it's still consistent to have this and have a sufficient annihilation and evade, given the limits on the gauge boson of this sector. Once you give it a mass as well through the Stückelberg trick. Once given the constraints, I won't go into it, but it's viable to get around to be consistent with direct detection constraints, because as we talked about yesterday, you'll have some processes like this, where there's a kinetic mixing here, and to the visible sector photon. And so you'll get certain scatterings like this, which can be picked up in detectors, okay? The current constraints discussed in the notes, references given, comes from a dark side 50 collaboration.
I have a question. Why this ratio of omega dark matter to omega barium is independent of the efficiency factor?
The efficiency factor, in terms of reprocessing of any, because whereas basically the efficiency factor here with this with approximations with this far out of equilibrium decay of the little phi, this is like 1. So there's no, and this is occurring, we're assuming this is occurring at temperatures below the electroweak phase transition. So there's no reprocessing of the baryon charge into lepton asymmetry.
So it's independent of CP violation and things like
the masses, at the end, because I mean the yield, you have to make. I should say, okay, you have to check that I gave a formula for the CP violation yesterday. Given that formula, you have to find some parameter space where everything works. So in principle, okay, for example, there's in the original paper, they give an example where M phi, let me put some numbers, 2000 TeV, this long-lived scalar, average 1x produced in each decay, and they assume that gamma phi is of the order of M phi cubed on 4 pi reduced Planck mass squared, okay? This is a choice. You can vary this. It just has to be long-lived, You can vary this, what suppression you put here, okay? And in the end, it comes out that T reheat is low, but still a little bit above BBN, so you think hopefully you're safe, You can go a bit higher, if it's uncomfortable. And in the end, if you put in the numbers, then eta B is about 2.5 times 10 to the power of -7 epsilon. Epsilon, I gave the formula yesterday. And the issue there is that this is a bit aggressive, because then you need somewhat large couplings in like a little, not far above 1, but sort of largish couplings. If you look at that formula for epsilon I gave yesterday. So also there's other parameters where smaller epsilon and M phi are possible. Okay. So that's how this sort of model works. And the reason why they're interested in this low scale, so in principle you could imagine, okay, why do they, why is there this complication with this long-lived phi? Why don't we just go to the thermal decays in a thermal bath? And the reason why they're interested in this relatively low scale is that to point out that in this sort of scenario, yeah, you've hidden the anti-baryons sort of you've hidden the anti-baryons in the dark sector. So you also get an exotic process known as induced nucleon decay. Okay? So in regular nucleon decay, you have something like let's say, regular nucleon decay would be like proton, so a nucleon going to a meson, which I'll denote M, plus, in this case, a neutrino, something like this. This is the standard processes of nucleon decay, where you have typically some grand unified theory with a baryon number violating operator at a high scale. But here, we have induced nucleon decay instead. So we said we chose the masses so that the nucleon decay would be impossible kinematically in this theory. But we still have the dark matter particles around in the halo today. So what can happen is that if you have, say, a proton, which is made up of D, U, and U quarks, if this dark matter comes along, say Y in this case, hits this nucleon, then you can get an induced nucleon decay instead, okay? So we have the process here. In this example, I chose these flavors so that we'd get a K plus in the end, but other possibilities are also there. So in the end, we get these induced nucleon decays. In this case, phi, say Y P to phi star K plus, okay? So you can estimate the cross-section for this sort of process.
So sorry,
Yeah.
just for me to understand. So what particle is the dark matter? Is Y or Phi?
They're both dark matter particles, but here, for example, I've assumed that Y is they're both dark matter particles. So you both have them in the halo. So in principle, you have both possibilities. Yeah. For the initial state.
And the masses of Y and Phi are similar, or they're different? Or?
Yeah, okay, they're similar. They lie in this range, yeah? So, okay, I guess it's favorable to have the more massive one here, just for the...
So this is like an elastic dark matter, because you have two states.
Yes, exactly right, yeah.
Can be changed.
Yeah, and you destroy a proton or a neutron. Yeah.
Okay.
So instead of looking for this process in a direct detection experiment, you can instead look for it in experiment looking for proton decay, such as super Kamiokande. So if you don't know what super Kamiokande is, it's a big tank of like 50,000 tons or whatever in a mine in Japan, and it has photomultiplier tubes around it, and in the water it looks for if any protons or nucleons decay. Okay? By looking at the final states that give off, when the final states decay, they give off a pattern of photons which can be picked up in the photomultiplier tubes. Okay? It's also important for neutrino physics, this experiment. Okay, so now I really need to hurry up, but basically you can estimate this induced nucleon decay cross-section, and it comes out to be something like, just from dimensional analysis, and so you look what vertices and particles and propagators are involved, and you estimate this, and you have a nuclear matrix element that you need to estimate. But this is just estimated as lambda QCD for our purposes. Yeah. And lambda QCD is also of the order of the reduced mass of the nucleon and the dark matter, say. Yeah. So that's why this just drops down to lambda QCD. Yeah. Sorry. Here, this is capital M coming from the vertex from the first operator there. And this is the mass of this is like the mass of one of these, Dirac fermions, okay? So this turns out to be about 10 to the minus 39 centimeters cubed per second. If you normalize this to the TeV scale, so this is why they're interested in the TeV scale. Okay, and then the lifetime of your nucleon will just be the number density of dark matter times sigma V induced nucleon decay. And for these numbers, for this number here, this turns out to be of the order of 10 to the 32 years. Yeah? And the current limit, the limit on this decay is actually much stronger in terms of the lifetime. So the branching ratio, the proton lifetime divided by the branching ratio for this decay channel, given the super K constraints, should be above 5.9 times 10 to the 33 years. Yeah? So comparing this, you can say, okay, this shouldn't be TeV scale, this should be a bit higher. But there's a subtlety involved, because here, the kinematics are different. Yeah? So, for example, in the standard nucleon decay here, this is a two-body decay, and this has the momentum of the P of K plus. This is like 340 MeV. Yeah? While the momentum of the K plus here given the allowed masses and the velocity of the dark matter in the halo today, the momentum here is in the range 680 to 1360 MeV. So while and I should say, in Super Kamiokande, in this analysis, okay, the K plus has to escape the nucleon, and then it travels a bit, but it typically actually, they run a simulation taking into account that it's traveling through a medium and so on, and basically 90% of the K pluses would be estimated to decay at rest. Yeah? So this is important for their analysis so that they can look for these particles, yeah? So that they know that most of them decay at rest. So here's as far as I know, nobody's done the detailed work for checking, what happens if the K plus has a different momentum, yeah? So okay, maybe you say I have to push up this scale, or it could still be consistent, yeah, because of these kinematic effects. So this is sort of a sort of very unique signature of these models, and that's why I wanted to cover it. Okay. So that's all I had to say about asymmetric dark matter. So if there are any more questions on this, yeah.
So how does lambda QCD appear in this cross-section?
Yeah. So basically, you have to here, you have the interaction at the parton level. So going from the parton level, this is actually a bound state. Yeah. So in principle, you have a nuclear matrix element there to go from one to the other, and this is typically of the order of lambda QCD. Yeah. So then just from dimensional analysis, put the sigma v has to be scale is 1 on mass squared, some mass squared, yeah? So then you just put, I just put the required powers of lambda QCD there, yeah? In the paper, they discuss a little bit more, okay, the validity of this sort of approximation and so on. They say it's rough, but should give very approximate. Should be okay, very roughly, yeah. Okay, I was a bit slower than expected now, but I thought it would be good to actually, finish the topic, yeah, the asymmetric dark matter. So we've completed it in a bit more detail, okay? So now I'll try and be as efficient as possible, but still comprehensible to the students for the last part, which is just going to be, I'm just going to take and show an example of CP violating decay, okay? So we've seen examples before, but I want to give, for a simple example, show how to calculate it, yeah? So we're going to look at a different Lagrangian now. So we're going to have these scalars delta, which carry color charge, and we're going to couple them here to down type quarks of S and D. Okay, you can have different possibilities, but we're just going to consider S and D, and also to some neutral lepton, okay, and the up quark, right-handed up quark. Here we've seen this. We're going to use the sort of four-component spinor convention, yeah. And these fields here, this is just defined as charge conjugation matrix, psi bar transposed, okay. And we saw that this. We saw this in the Weyl representation, but just in any gamma representation of the gamma matrices, it can be written like this, where this is the charge conjugation matrix, and here you have the complex conjugate. So what this allows you to do is sort of write the antiparticle of this psi, the operator that creates the particle and annihilates the antiparticle, but without a bar, yeah, so that you can form these in terms of a Lorentz invariant quantity, yeah. So, okay. And then you have various relations, such as that psi r conjugate is left projection operator psi conjugate, and similarly psi L conjugate is right. This should, you can imagine here we're just applying the conjugation to the full unprojected field. Okay. Okay. So yeah. So what is delta? Delta here, we're going to have delta 1 and 2, and they're charged scalars. They're singlets under SU2, triplets under SU3, and they carry hypercharge. And NR is just going to be some heavy neutral lepton, let's say. Okay? Very good. And this is all, you can check this is all gauge invariant. So for example, here, in principle, there's a color index alpha with an contracted like this, epsilon, alpha, beta, gamma, alpha, beta, gamma, okay? And then, yeah, and here we just have some delta, alpha, beta, okay, for the color indices. Okay, so the decays, the possible decays this gives us is that delta I goes to dr bar sr c, yeah? But this is just the antiparticle of the strange quark, yeah? So more conventionally, you can think of this as giving you the decay d bar s bar, like this, yeah? So by using this conjugate field, we can get a Lorentz invariant operator which gives us this sort of decay, yeah? And similarly, di can go to nr and u r c bar, okay? Here, this is like delta I going to u and n. So this has final state baryon number -2/3, and this has final state baryon number +1/3, okay? So this is baryon number violating. So now you want to calculate, we want to calculate these tree level decay rates. So to do that, we can use a trick. The spinors are related in the following way. So we're just going to use the usual 4-component techniques, yeah? Okay? So this, if you use these relations in the expansion of these fields in terms of the momenta, you'll see that what spinors will appear here in the final states, yeah? So you can, for details, you can see, say, 0812.1594, Appendix G, or another good reference is a review article by Harbour and Kane from 85, okay? So even basically, when we use these tricks, we can make the charge conjugate matrices disappear from our Feynman rules. So that's why I also write, okay, even though this is the anti-S quark, we'll have like a spinner appearing here in the final state that like you would with a particle normally, yeah? And this shows, this is this arrow convention as well, okay? So you can check that, say, this decay rate, the tree level decay rate here, you can check that this is just so let's say we're interested in delta 1. So we have a 1 here. This is just the matrix element. Okay? And the complex conjugate will be negative I, y d1 star. And then you have to take the Hermitian conjugate of this. And you get that just using the properties of the gamma 5 matrix, which appears in this PL and PR, 1/2 1 minus plus gamma 5, okay? So you can check this, that you get a left projection operator here and a U, this should be PS, momentum of the S quark. Okay? So there are other ways of handling these charge conjugation matrices. But this is, for us, an efficient way here for this problem. Okay. So then you sum over spins, calculate the matrix element, absolute value matrix element squared, and you should find as an exercise that this in the center of mass, when you go in the center of mass frame, well, any frame, but you find that this is 2 PS dot PD, and that this gives you y di squared m delta 1 squared. To do this, just write these in the rest frame of the delta 1, and then you'll find that. Okay. So this is our matrix element squared, and so then the decay rate d1 to d bar s bar. This is 2. This is we have in principle here. We can choose, if we start off with this one color here, we can have, 2 choices of the possible color choices here, 2 combinations. So this gives us a color factor here, m delta, and then you look at, say, the appendix of Peskin and Schroeder, and then you should find this formula here. 2 final state. The final state particles are treated as massless, okay? Okay, so this gives us then just y d1 squared m delta on 8 pi. And the other decay rate, you don't have this, everything is the same up to, and we're also ignoring the mass of this particle here. So in the end, gamma delta 1 to, what is it? This is UN. You have everything the same, a different Yukawa coupling, but you don't have this color factor. So you'll just end up with a 16 pi, okay? These are the tree level decays, just to remind you, just to show you how to, nothing mysterious is going on with these charge conjugation matrices and conjugate operators. Okay, so now, so now we want to consider the interference term, d delta 1. Okay, we had the y d1, sr c dr bar, and then we're going to have a loop level diagram like this, and we're going to put a delta 2 here, and this will give us here the same final state. And in the loop, we have an R and UR C bar, okay? And we're going to give these momenta here. We're going to label this PU, and this is going to be, we're going to choose this to be the initial form momentum minus K, where K is the momentum running in the loop, which we'll soon see. And Pn, we have to conserve momentum at this vertex here. So this will be Pi on 2 plus K, okay? Then we have YU1, YU2 star, YD2, okay? Okay, and this is okay. This has to have the same momentum here. Okay. So this is sort of similar to one of the loop diagrams we saw from in the leptogenesis example yesterday. Okay? So the general structure is as follows. We want to consider something like gamma. We want to consider the difference between this decay rate, which has the following structure. If you look at the diagrams and find the couplings which appear, we saw something very similar in the leptogenesis example yesterday, yeah? And now here you just have the, instead of having this diagram and this diagram star, you have the contribution of this diagram interfered with this diagram star. Yeah? So you just get the complex conjugate, YD1, YU1, YU2 star, YD2, ITL star. Okay. And I skipped over one thing in the interest of time. You can look at these couplings, just choose here one generation, so the first generation quark U, here the first generation D, and here the second generation S. Do the rephasing analysis, and you should see that there's a physical phase. Yeah? So this combination of couplings has a phase which can't be removed, okay? So this is from the interference loop tree. And here, gamma, now let me call it tree loop. This is for the charge conjugate. So as Toma argued yesterday, you have here these couplings appearing again, but now it's the CP conjugate, so it's the complex conjugate of the couplings above, but the kinematic factor here is the same, okay? And then you find here, you'll have YU1 star, YU2, YD1 star, ITL star, yeah? Okay, so then you find the difference. This is also, you can also see the book by Kolb and Turner. They have a toy example, which discusses this, okay? This structure, exactly. Okay, and then you find this difference, and you find that this is equal to -4 imaginary part of the couplings, which we argued has a physical phase, YU2, YD2 star, and the imaginary part of the interference, the kinematic part of the interference diagram, okay? So, very good. So now you can check that this diagram here, the loop level diagram, once you so our task here, this you can check that there's a physical phase that's known, so we want to know this difference, and now we're going to calculate this, okay? And we have half an hour, so I think we can do it. You can check that you get something like this. So use what you know, what you've learned about from the Feynman rules. Here you have a closed loop of fermions. So you check the Feynman rules for that. You have to trace over these propagators and take the minus sign, all right? And that gives you this following factor, Pn dot Pu, where these are these four momenta, and you have to integrate over the momentum k, yeah, because you have this loop. And then from the fermion propagators, from the denominator, okay, we have a momentum squared, yeah? And these, we're assuming these are massless, yeah? Otherwise, we would have Pn squared minus Mn squared and Pu squared minus Mu squared, okay? And we also have this propagator here, which has momentum Pi squared, but Pi squared minus the mass squared minus M delta 2 squared will give us just M delta 1 squared minus M delta 2 squared, and then I've cancelled off a sign here, all right? So that's why you get this term here in the denominator, okay? Very good. So there are a few additional, steps given in my notes if you want to go through it. If you want to check all the factors of I and 1/2 and so on, yeah? no guarantees that I got all the signs correct and all the factors of 1/2, but I tried to be as careful as possible. Okay, so now we have to write, yeah?
Regarding the diagram that you can write about the vertex correction,
Yes.
This does not contribute to the asymmetry or not? Because you can
is there a
write
vertex?
down one and calculate
I don't
the
think there's
interference.
we can check this later. I don't think there's a vertex correction in this.
Okay.
This one,
Well,
yeah. So it's simpler than in leptogenesis.
Yeah.
But we can check later to make
Right.
sure.
Perfect.
Yeah.
Thank you.
But, okay. So now we're just going to take ML and multiply by MT star, which we had before, yeah, the tree level one. Take the spin sum. So from T star, we have something which, when we take the spin star, you know, we can write this as a trace of various products of gamma matrices, yeah, and drop the couplings, yeah, because we're only interested in the kinematic factor, right? So then, in the end, okay, in the kinematic factor, we still have this. We'll have from our matrix element. Now we'll have here some MT star ML, okay? The contribution to the decay rate. But we have all this, we'll have this integral over the final state momenta, yeah? So I'm gonna drop this, yeah? So what I'll write is that I'll write ITL is equal to 1 on 2 M delta 1, okay? We're gonna put in the color factor in the end, so that's just this. And then this phase space integral, okay? I'll just imagine all this, I don't know, call this D phase space, yeah? All this stuff here. D phase space. I just don't want to write it everywhere, right? And then times ITL tilde, yeah? And we're interested in the imaginary part of this now, yeah? So then, if you do that, you find that taking the spin sums, you should find that imaginary part so all this stuff, we get a similar factor out here due to the, as we did when we did the tree level diagram, yeah? But we still have here this, this momentum integral. And we're interested in the imaginary part of it, yeah? Okay, and now we can do a trick. We can use the so-called Katkowski rules. So instead of evaluating this full integral here, because we're only interested in the imaginary part, we can apply these rules, yeah? It's an algorithm, yeah? You can see Peskin and Schroeder chapter 7, okay? It's related to the optical theorem, okay? So, number one, we have to cut the diagram. With cut propagators being allowed on shell kinematically, yeah? So here, delta 1 is much heavier than N and U, right? So we can cut the diagram here. We'll cut the diagram here, and these propagators can be on shell, okay? In the leptogenesis example, we also had a self-energy diagram like this. Put the cut there, and we had a triangle diagram which doesn't contribute here, but in the leptogenesis case, we can cut there, yeah? In the triangle diagram. Number two, you replace the denominator part of the propagator. So in the scalar case, it's, this is the propagator, but there's an I and the top. And in the fermionic case, it's when you, just take the denominator, right? If you you start off with 1 on p / minus m, and then you multiply by p / plus m on the top and the bottom. You get a p, and then you just get this on the denominator like we have here. But our propagators are massless, okay? And you can replace this by negative 2 pi I times a delta function, where the delta function forces the propagator momentum to lie on shell, okay? Replace this for cut propagators. Okay? And 3, sum over all possible cuts. Okay? And when we do this, this will give us exactly this whole thing will give us this gives us 2 times I times the imaginary value of what we were interested in. Yeah? Okay? So now we have this here. Okay. So we're going to apply this and find that equals, what do we have? Negative m delta 1 should be. Yeah, m delta 1 squared on m delta 2 squared minus m delta 1 squared 2 pi I squared from the Kutkowski rule number 2. Now we have d4k on 2 pi to the 4. And this here, just from the numerator. And now the denominators we can replace with the delta functions. Delta Pn squared, delta Pu squared, okay? 4 momentum squared. And we remember that Pn is Pi on 2 plus k, and Pu is Pi on 2 minus k, okay? Now we've simplified this, but now there's a useful trick to deal with these delta functions, yeah? And for that, we have to rescale, do a change of variables of this k, yeah? So the trick is the following. You can check that it works. First, you rescale k, right, to get rid of one of the pi's here. And then you'll have a d4 k prime, yeah? Then the d4 k prime, you can just relabel to d4 pn, say, yeah? If you rescaled this one. Then we want to introduce another integral now over pu and put an overall delta function enforcing the 4 momentum conservation. So the trick boils down to, you can check that this is legitimate as an exercise, yeah? But intuitively, you should see that, okay, it sort of gives us what you expect. So this integral over the 4 momentum is now, k in the loop, is now replaced with 2 integrals over these momenta times this delta function, which enforces precisely the 4 momentum conservation at the vertex, okay? So this is a useful trick in a lot of calculating these cut diagrams. Okay, so in the end, okay, then we get that this is m delta 1 squared on m delta 2 squared minus m delta 1 squared d for Pn, d for Pu on, okay, I cancel off some of these factors of 2 pi. So we have a 2 pi squared here. Pn dotted with Pu, delta Pn squared, delta Pu squared, and now we have this 4-dimensional delta function, Pn plus Pu minus Pi, okay? And now we can use this form to do the integrals over these delta functions. Say take the energy part of this, yeah, the 0 component. And all that's going to do is enforce that En is on shell, yeah? And because it's massless, do A integrals over the delta functions, yeah? So that enforces this. EU is this, okay? But because this is Pn squared, when you use the properties of the delta function, you'll find a 1 on 2 En and 1 on 2 EU. And in principle, there's also a negative energy solution, but this won't contribute because of this, the energy part of this delta function here, which forces this to be on shell, right? So P initial is M delta, so these then have to be positive eventually. Okay? So then doing this, we have this prefactor again. Now we've done this. Now we have three-dimensional integrals left over here. d3pn, d3pu on 2 pi squared, pn dotted with pu. And now from the properties of the delta function, we get a 4pn pu on the denominator. Okay, these are just the energies here. Yeah. Okay. Whoa. Okay, very good. Now we do say the d3pu integral using this delta function here. Okay, and this just enforces that pn is equal to negative pu. Yeah. Using d3 pn plus pu equals to minus 0, yeah, because the 3 momentum of our initial particle is 0, yeah. Okay, so that this integral will enforce this, which means that pn dot pu, which is the en eu minus pu dot pn, that this will just give us 2 pn pu, okay? Sorry, this enforces that, yeah, of course, this enforces this minus sign, so there's no cancellation here, yeah. Okay, very good. So you get a factor of 2, not 0, yeah? Okay, so very good. Then, having done this, we're almost finished here. We get to delta m collecting factors of 2 and so on. M delta 2 squared minus m delta 1 squared d3 pn over 2 pi squared. And now I just rewrite this last. So we did the integral over the d3 part, and now we're left with the energy part of this, right? And this is just 2 pn minus m delta, yeah? Okay? So this, of course, is just using the properties of the delta function. This is just delta pn minus m delta on 2 divided by 2, okay? So then, okay, good. D3, did I miss a factor here? Yeah, I've missed a factor here. This should be, So pn.pu. Yeah. So you see here, we got a 2pn-pu, and that cancels with the denominator here. And there's a 2 on 4, so you get a factor of 2 here. Okay? Okay. So, very good. Then we're left with imaginary part of ITL tilde is equal to m delta 1 squared on 4 pi Did I miss a factor? Anyway, let me check afterwards. M delta 2 squared minus m delta 1 squared. So there's a 2, there's a 2. Did I miss a factor of? No. Okay. Let's check later on. Yeah. When we go from this d3pn integral, we're going to rewrite this as here. As d3pn, we're going to rewrite this as 4 pi pn squared dpn, okay? So then when you group things together, you'll find the overall factor here, okay? And then we'll have an integral dpn pn squared delta pn minus m delta on 2, okay? This is, of course, just the energy squared of the n. Yep. Okay. So then we can evaluate this with the, do this integral, and you relate the Pn to the m delta, and you get m delta 1 to the 4th power here. 16 pi m delta 2 squared minus m delta 1 squared, okay? Then imaginary ITL is going to be 1 on 2 m delta 1 integral d omega on 4 pi. We can integrate over the entire solid angle, so this just gives us 1 on 8 pi to final state momentum over m delta, because the particles are massless. This factor here also gives us 1. And then imaginary part of ITL. So this gives us m delta 1 cubed over 256 pi squared m delta 2 squared minus m delta 1 squared. Okay. So remember the color factor times 2 for color, for the possible final state colors. And then in the end, using this and the results previously, we end up with the result gamma delta 1 to ds minus gamma delta 1 to ds. Putting everything together, we find that this is negative imaginary part yd1, yu1 star, yu2, yd2 star, m delta 1 cubed on 32 pi squared m delta 2 squared minus m delta 1 squared. Okay? Now, so that's sort of what we set out to calculate. Now, if you give me a couple more minutes, I can relate this to epsilon parameter that we're interested in for considering baryon asymmetry. Okay? So consider the CP violating decays that we have in this theory. ds bar this we write as some overall gamma 1, the partial width, but because it's CP violating, there's a little deviation here compared to this one, okay? This is just by definition. Delta 1 to nu. Okay, now use the fact that by CPT, the total decay widths have to be equal, yeah, of the delta 1 and its antiparticle, yeah, delta 1 star. And then you should find that gamma 1 d, so the partial width times this parameter parameterizing the CP violation, that this is related to the CP violation in this decay channel, yeah? So there's no need to calculate this separately, yeah, because we've already calculated this part, yeah? So, very good. And by by our definition of this here, you should see that what we've calculated on the left there is 2 gamma 1d epsilon d. This is what we calculated. Okay? So now we're interested in the net baryon number we produce, yeah, in each decay of. So imagine we start off with 1,000 deltas and 1,000 delta stars, yeah? Delta 1s and delta 1 stars. And then we just put them in a box out of equilibrium and let them decay, and we want to know how many baryons they produce, yeah? So, a useful quantity which appears in the Boltzmann equations is the net rate of B creation, yeah? Through the decays of delta 1s, yeah? And this is just given by sum over the final states. So you weight each final state with its baryon number, and then take into account that you have both deltas and the same number of delta stars initially, yeah? So you can see that this it gives us then the first final state will give us gamma 1d, 1 plus epsilon d. So this is to the d bar s bar, yeah? So baryon number negative 2/3. Minus, yeah, overall baryon number, and then, yeah, okay. Gamma 1d, 1 minus epsilon d. And then we have the other final state, gamma 1u, 1 plus epsilon u minus 1/3. Did I do this correctly? Probably missed the minus sign. Yeah, here I missed the minus sign, yeah. Plus, minus, yeah, okay. Okay, and this becomes negative 4/3 epsilon d gamma 1d plus 2/3 gamma 1u epsilon u, and then use this relation here, and you see that this is exactly to negative epsilon d gamma 1d times 2, which is just what we calculated over here, but with a minus sign, yeah? So then, now, we take here this is the total decay rate. So we take it over the right-hand side, and then I write the last formula of the lecture, which take the gamma d on the right-hand side, okay? And then we'll find that epsilon delta in this case will just be imaginary part yd1, yu1 star yu2, yd2 star m delta 1 squared over 2 pi. So in the denominator we put the total width, so we get some factors like this. And remember the tree level decays had like factors of 1 on 16 pi in them. And this one had a factor of 2 for the color. And then we're done. Okay. Okay, so this is the epsilon d, but remember we still need a departure from thermal equilibrium to produce an asymmetry. So this is just one part of the calculation, yeah? So in the end, yeah. So I just want to mention one thing. What helped me a lot, I didn't have time to cover sort of relations between matrix elements and from S matrix unitarity. But what helped me a lot when I was learning about baryogenesis, I can recommend this paper by Kolb and Wolfram. It's just a very generic setup explaining, baryogenesis from decays, and of course, leptogenesis is perhaps the most relevant realization today. So this paper here, Nuclear Physics B172 from 1980. So I didn't have time to talk about those details, but I thought I'll just mention it. Okay, so thank you very much.
Thank you, Iason. By the way, this is the same Wolfram as in the Mathematica Wolfram. He was a high energy physicist before becoming a millionaire with Mathematica. So, any questions for Iason? Just a second. Just a sec.
Yeah, very good.
What about this difference in the mass in the denominator?
Yeah,
Can you explain a little bit more at this point?
Yeah. So when the masses get very close together, yeah. So we had this sort of diagram: delta 1, loop, delta 2, and then decays, yeah. So then you can see that if you take this mass splitting to be smaller and smaller, you increase the CP violation, yeah. But you have to be careful. There are other effects when you take them really close. It's like you have to also take into account the finite widths, yeah, which aren't included in the way I've written this. So this has been studied extensively in the case of resonant leptogenesis, where if N1 and N2 are very close, you can get this resonant enhancement. Yeah? But if you take them really close, the way you treat them in the Boltzmann equations needs some care. Yeah? I don't know if Toma has any comments more. Yeah.
Okay.
Yeah. Then. Yeah.
So stay
Yeah.
tuned for the next lecture.
So here, this will hold. Yeah. You can see that if you take this arbitrarily small, you'll get some epsilon delta, which is larger than 1. You see something's gone wrong. Yeah. So you have to take into account the finite width, and then all sorts of effects become important, which regularize that.
Okay, so I don't see any. Yes.
Do these sorts of decays like mess up with BBN at some point, or like is there some bounds or something like that?
Yeah, if you need the baryon asymmetry to be generated before BBN. Yeah. So in this scenario, could be some high scale thing. Yeah. You also have the issue here that I use this decay in a paper, but we were considering a strong phase transition which put delta 1 and delta 1 star out of equilibrium. So that's how, because these things also carry color charge. So, I mean, if you write down the Boltzmann equations, you also have to take into account their annihilation into gluons, yeah, which is CP conserving. So you have, but in principle, if the scale is high enough, these could source a baryon asymmetry. You also have a problem with the N, yeah? So this was just a simple example of calculating CP violation, but you have a problem with this N, because if you give it couplings to like leptons, yeah, if you make this the right-handed neutrino and so on, then this, or it can also, if it has a Majorana mass, it can lead to washout of the asymmetry because it mediates then delta L equals 2 interactions while the sphalerons are still active. And if not, then it carries sort of it also carries B minus L charge. So then if it's coupling to the neutrinos and it's a Dirac particle, then you can assign it standard model lepton number. And then this whole thing, then you'll also get, this thing then no longer violates B minus L. So then you also don't generate an asymmetry at high scale. So so this isn't of like a full theory, just an example of how to calculate the CP violation. And yeah.
Okay, more questions for Iason? Okay, don't see any more questions. So let's thank Iason for this very nice set of lectures. So I want to ask people that have already put posters